Okay, Ruby Taiwan, let's get going here with JRuby, Ruby on the modern JVM. I'm going to talk to you about JRuby today. My name is Charles Nutter. I've been a JRuby core developer since 2004, so around 20 years now. I've been doing this full time since 2006. Hope to be able to keep that going for a while. There's my contact information if you need it. So we're going to talk about JRuby today. So what is JRuby? Some of you may have heard of it. Some of you may even be using it. Simply put, JRuby is Ruby on top of the Java virtual machine. We focus on making it a Ruby implementation first, and then the fact that we're a JVM language means that we get other benefits from the JVM ecosystem. So ideally, we want your Ruby code to just work with a few minor exceptions. We don't support Ruby's C extension API. We have our own API for doing that. We don't support forking because the JVM doesn't support forking. And then we do get newer or advanced features from the JVM like parallel threading, better garbage collection, just-in-time compilation. We'll go into some of those a little bit later. But JRuby is the most successful of any alternative Ruby implementation. Over the years, we've had thousands of production users. There's probably thousands of production users out there right now. 15 or more years of real-world use, and really the only Ruby implementation that's ever seen large-scale production deployment other than standard Ruby. So what do we believe is important when building a Ruby implementation? Well, these are a few items that I thought I'd pull out. First of all, it needs to be usable. Usability is important. We want it to be compatible. Ruby features you expect to work should work the same way as on regular Ruby. Ideally, it should start up quickly. When you're running an application, it should warm up and be full performance as quickly as possible. And these are all challenging areas that we continue to work on all the time. You should have a good set of runtime features, and that's things like having solid garbage collection that you don't have to worry about, just-in-time compilation that will optimize your code as it executes, tools for monitoring and profiling and debugging, good libraries, good runtime VM support for concurrency. And this is all the kind of stuff that we get from JVM. There should be a good set of platforms that you can deploy on. You want to be able to deploy mobile applications or server applications. You may want to be able to do graphical applications on a desktop. You want to be able to integrate in with larger applications that are deployed across many systems. You want ease of deployment. And these are all areas that we focus on with JRuby too. And then, of course, performance, which means a lot of things, many different things to different people. Sometimes that means straight line performance, running a single particular piece of code as fast as possible. Other times that means scaling, using all the cores in your system to get as much concurrency as possible. When handling concurrent requests, being able to get work done in parallel, using all of those cores without having to spin up lots of processes and waste resources. And different applications are going to need different capabilities. So you should always approach your tools like Ruby implementations with an understanding of what your application needs. So getting started with JRuby. This is a shot of the JRuby homepage. You can, of course, just go download a tarball or a Windows installer. The only real prerequisite for JRuby is that you have Java installed. There are packages for all of the Linux implementations, easily downloadable installers for Windows. We recommend that you use whatever the latest Java is, and we always try to test on that latest version. But currently, Java 8 is the earliest version supported for JRuby 9.4. And then install JRuby. Usually we recommend you just use a Ruby installer like RVM or Ruby install. Sometimes there's a system package that you can use to install JRuby on Debian, for example. Or there's Docker images that we publish with a wide range of different JVMs. And then, of course, there are tarballs. There is the Windows installer if you just want to go and manually install it yourself. And then test it out. This is a little example switching to JRuby and running IRB. And then we call the Java runtime class, which lets us access things like available processors and free memory. And note that this looks pretty much just like Ruby once we have that runtime object. We use underscores instead of the camel case of Java. And there's lots of other little niceties that we've done to make calling JVM code, calling Java code, feel like it's just regular Ruby libraries. So compatibility was a big part of my priorities here. JRuby 9.4, the current major release, is compatible with Ruby 3.1. About 98 to 99% of all the language specs are passing. There's a few minor things that you'd probably never notice. We may implement them, but sometimes we kind of just want to wait and see if anybody needs those features. We also have a nearly complete compatibility of the core classes in the standard set of Ruby classes like string and array. And we support all of the same pure Ruby standard libraries that regular Ruby does. Some of the standard library has extensions, and where it's important, we have made ports of those for JRuby so that the features are still there. There's also JRuby 9.3 if you need an older Ruby compatibility. We have kind of stopped maintaining it at this point, but we would be willing to do targeted work on that if your company needs something specific. Always focusing on compatibility before performance. So catching up with Ruby 3.1 was a big help for us leaping forward. That's helped us take a step back and start looking at more performance and optimization over time. Here's a little chart from the Ruby specs stats page. This kind of shows where our compatibility level is. Very high level of language and core library compatibility. Standard library drops off a bit because there's a few little used and unusual libraries that we don't have native versions for JRuby. But fully covering all of the various security specs, security regression specs that are there. And we always keep bumping these numbers up with every release. So, all right, I mentioned runtime features being important for a Ruby implementation. So let's first talk about garbage collection. The JVM is legendary for having the best garbage collectors in the world, made to handle small and fast throughput on a heap, or very large heaps with huge data sets, terabytes of memory. All of that can be configured in the JVM garbage collectors and available to you on JRuby. There are at least 3 or 4 different garbage collectors that are shipped with standard OpenJDK. The ones I'm most familiar with are the parallel collector, which is kind of the fastest throughput, fastest allocation rate. If you're creating a lot of objects that are very short-lived, that can be the best one. And then G1 and ZGC, newer garbage collectors that help work with very large heaps without slowing down your system and causing garbage collection pauses. This is an example tool that's available for the JVM. This is a free tool called Visual VM. And on the left, you can see it's monitoring the CPU usage of the application, the amount of heap space that's being used, number of JVM classes loaded, number of threads, basically high-level information about the runtime. On the right, we're seeing a live view of a Rails benchmark. And this is actually showing the different heaps that the GC has set up. And we can watch them slowly get filled with garbage and then get collected, and then the process repeats. If you see nice sawtooths like we have here, then the GC is keeping up pretty well with the amount of garbage that's being created. If you see a steady increase over time, then you may have some sort of small memory leak, and there's other tools that can help you investigate that. So just-in-time compilation is the other big area that we benefit from on the JVM. The JVM that's shipped, the JIT that is shipped with OpenJDK is called Hotspot. It has 2 different tiers, the C1 client tier that does some quick optimizations, and the server C2 JIT that runs longer, gets more information about your application, and then does a much more aggressive optimization. Both of these are typically running without any configuration, so you should get initial performance very good, and then over time it will increase as it learns more about your application. There are other JITs available out there. For example, the Graal JIT, which can be plugged into OpenJDK or downloaded as a separate build, does some more aggressive optimizations, newer, more interesting ways of optimizing JVM code. We're seeing some good results from this that I'll show a little later on. And then there's other JVMs like OpenJ9 that have their own JIT compilers with interesting features like saving off the optimized code between runs so you can start up quickly next time, putting a server in the background to help JIT code across many instances, and something called CRIU, which allows you to save a snapshot of your application. And I'll talk more about that later too. And then the tooling that we get with the JVM, monitoring tools, profiling tools. Of course, I just showed you Visual VM, one of my favorites, has lots of plugins and it's freely available. The JDK also ships with a built-in feature called the JDK Flight Recorder. This is a very low overhead profiler that allows you to monitor even production applications with only perhaps 1% overhead. If you want to gather a bit more information in a development environment, you can turn on more features and it still tries to keep that overhead pretty low. The tool that you use to view these recordings is called JDK Mission Control, and this is a graphical client that brings up flight recorder data. So here's an example of starting a flight recording for a JRuby server. Once we have that run and we've gathered that recording, we can dive in on things like objects on the heap. Here you can see things like Ruby hashes, Ruby strings, the framing that JRuby uses internally. Ruby hash allows you to track where objects are being created in your application and determine whether you're churning through too many objects, whether you're creating large objects and throwing them away. Basically let you profile where all the memory is going so that you can investigate in your own application. We also can do profiling of methods, including Ruby methods. Down below, you see a few of the internal JRuby methods like Ruby module, checking the method cache, hash maps, method information, lambdas. All of the stuff that makes JRuby run internally is here. But as your application runs, those methods will also show up in this profile, and you can monitor and profile Ruby application right alongside the rest of the JVM. There's also a view of what threads we're doing. You can see many different threads that we're running in this server. The green indicates that it was executing. I believe the yellow here indicates that it was idle for that amount of time. That lets you see whether you've got threads blocked, whether you are getting the work done that you expect to see in a typical application. All right, so let's talk a little bit about performance and scaling, which is a different aspect of performance. So scaling applications. This has been a classic problem on standard Ruby. Because we don't have concurrent threads, we have to spin up worker processes to make the most use of all the cores in the system. Now, there's a lot of good tricks like copy on write and pre-forking and lots of servers that work very hard to reduce the size of those processes. But no matter what, you're still spinning up a separate process that has its own heap, that has to do its own garbage collection, potentially its own just-in-time compiling, and that wastes resources. You're duplicating a lot of state, duplicating a lot of work, and wasting a lot of time. JRuby is probably the best solution for this. You can take a single process and run as many concurrent requests, as many threads as you want through that single process. A single JRuby instance can run your entire site. You don't have to spin up workers and manage them. You don't have to scale out so much memory just to handle additional requests. You also get the benefit of these leading edge garbage collectors, which are designed to work well with a single large process. So all of these requests running in the same process gets better use of the system by having one GC that can manage it all. So for this little benchmark, I'm running a baseline Rails application. I believe this is a Rails 7 application. It's just a standard scaffolded blog app running on PostgreSQL with the Puma server. We just recommend using Puma if you want to run with JRuby. It works just fine. Running on an IBM VPC with 8 virtual CPUs, 32 gig of memory, and comparing JRuby 3.2 in this case. 3.3 is a little bit faster, but not a great difference in these numbers. And so since there's no concurrent threads, we have 16 workers for JRuby and 16 threads for JRuby. And then the data, just as a caveat here, the database, the benchmark driver, I'm using Siege, also running on that same instance. So there's a little bit of overhead from those two. All right, so let's see what kind of results we get here. So you can see, first of all, JRuby does start out a little slower. The first few iterations are going to take a while to warm up as we load in the code, as it runs for a while, and it gets compiled down to JVM bytecode and eventually native code. But very quickly, JRuby jumps out well ahead of standard Ruby, even using the new YJIT just-in-time compiler. And this is a pretty typical result. We are starting to get bottlenecked on database here. There's a lot of objects being created, but JRuby generally will win on overall requests per second and latency for a Rails application. We look at this a little bit differently. Here is our peak requests per second. Of course, higher is better here. And again, you can see JRuby is out in front of JRuby with the YJIT. Now, this really doesn't tell the whole story. It's important to look not only at how many requests per second you're able to generate, but also how much memory is required to do it. So JRuby, without any configuration, the JVM will just try to use as much memory as you've got available. It likes to stretch its legs. We can configure this down to have only a 300 megabyte heap, which results in a little bit smaller than a 1 gigabyte process. We can also use different garbage collectors that are more efficient about memory use. JRuby using the G1 garbage collector, using about half as much memory as running with the parallel collector. On the other hand, we've got JRuby. 16 instances of that are already 1.6 gigabytes. With YJIT doing its magic and compilation, that bumps up a bit, and now JRuby is actually quite a bit larger than the two tuned JRuby instances. And so what does this actually translate to? So here we've got a comparison between JRuby 9.4 with no extra memory configuration, JRuby with and without the JIT, and then JRuby with configuration to run in a 300 megabyte heap. And notice we lose a little bit on requests per second, but not a whole lot. And now we're using about a third as much memory. Now, what gets really interesting is if we look at the requests per second versus the amount of memory we're using. So in this case, JRuby, with its slightly less than a gig of memory being used, is getting about 1.72 requests per second per megabyte of memory that you give it. That's already way out in front of JRuby. And what if we wanted to bump this up 10 times more concurrency? Well, it just continues to turn in JRuby's favor here. Now we're getting 13.7 requests per second per megabyte. Remember, we don't have to spin up extra processes. We can use one JRuby instance. So if you need a lot of concurrency, JRuby very quickly can save you serious money by not having to throw more memory at the problem. Memory is really where a lot of hosting costs go these days. Okay, so let's talk about some fun stuff here. GUIs, graphics, and games. So one nice thing about being on the Java platform is the wide array of graphical user interface libraries we have. The most commonly known is Swing. It's the one that's built into the JDK. It's a very clean interface, clean set of widgets. It's cross-platform and works very well. Easy to build, quick and simple user interfaces, fields, labels, buttons, typical set of widgets that you're probably used to from other frameworks. There's also another toolkit called the Scalable Windowing Toolkit. This is used by the Eclipse platform, Eclipse SWT. This actually wires in all of the native widgets. So on Windows, you're going to have buttons and fields and so on that look exactly like Windows. When you run on GTK, it's going to look like GTK widgets. If you run on Mac OS, it's going to look like the standard Mac OS buttons and UI elements. It also comes with a browser component based on WebKit, so you can embed a browser into your JRuby GUI application. And there's a really rich ecosystem of people building things on top of SWT. There's also another more unusual toolkit called JavaFX. This is a scene-based system, sort of like if you've ever played around with the old Flash applications that you would see on the web. Vector-drawn images, so they scale well, an event-driven UI library. And we have support for this via our JRuby FX project. So let's take a look at a few higher level libraries built on top of these. First of all, the Shoes library, designed to make it easy for people to learn Ruby and build simple graphical interfaces. The version 4 of Shoes actually is a JRuby based library, and it uses the standard Swing components and canvases to provide all of the features of the Shoes graphical DSL. Now, Glimmer is a more modern implementation, a more modern DSL for doing graphical applications. And the backend that it has for JRuby and SWT is probably the most mature these days. Here's a little screenshot of a Tetris game that was built with Glimmer. Very nice toolkit, really full featured and under active development today. Really nice if you want to build a graphical interface, build an application you can deploy across platforms with JRuby. Definitely would check out Glimmer. And then a quick little slide for JRuby FX. You can see how we kind of lay out in a DSL nesting format. We have laying out a scene. We have a group of objects. Within that group, there is a rectangle. The rectangle has some animations in it. This is using the JRuby FX wrapper around JavaFX. And what you get as a result is accelerated vector-drawn graphical components that you can do a lot more flexible things with than typical GUI widgets. So now I mentioned mobile as a target for Ruby applications. And yes, you actually can build Android applications in JRuby. We have a framework called Rubato. You can check that out on GitHub. This is actively being used for commercial applications today. You can use the standard Android GUI builder, just wire it up with Ruby code and build your entire application using Ruby. It's been a bit neglected, but it's being updated for JRuby 9.4 right now. We're hoping to have a new release of the toolkit out, but you can run off a branch very easily. We also have a demo application for this called Rubato IRB. Here you can see I'm actually using a interactive Ruby console on an Android device. This is not currently in the store. We used to have it there, but it turns out when you have an application that demands all permissions, they kind of frown on that. So we will republish this soon using the more current, the modern way of doing permissions on Android. But you can search for these APKs and install them. You'll need the Rubato core and the Rubato IRB APK. Now, like I mentioned, we are updating Rubato with JRuby 9.4. It works well. We've got the proof of concept is functional now. Here's just running through a few little simple graphical examples. If you're interested in checking this out, go to the Rubato project, the Rubato organization on GitHub, and look for the JRuby 9K proof of concept repository. So now it's not all wine and roses here for JRuby. There are challenges along the way. One of the biggest ones is, like I mentioned before, startup time and warm-up time for applications. So let's talk about startup first. The JVM is an amazing runtime, but it's just not designed to start up quickly. Almost all of the core Java libraries start out interpreted. It takes a long time for those libraries to optimize, and then we actually make it worse. So the Ruby parser, the compiler, our interpreter for our compiled instructions also are interpreted by the JVM. We do eventually turn Ruby code into JVM bytecode, but then that bytecode takes a while for the JVM to optimize as well. So let's take a look at the architecture of Ruby here. We have our Ruby code coming in on the left. That gets parsed and compiled into our Ruby instructions, our intermediate representation, IR. And then for a while, we will just interpret that IR. We want to get things executing as quickly as possible. Once we determine that a piece of code is hot or being used heavily, then we will turn that into JVM bytecodes. Those JVM bytecodes then get interpreted by the JVM and eventually turned into native code. And this goes around and around for a while it gathers information and works to optimize Ruby code into the fastest native code that it can. So how does this translate to startup? Well, it can be a little rough. Without any tweaks, JRuby starts up many, many times slower for a simple command like -E1. Most of this is actually because we have to load Ruby gems each time we boot, and that means our cold, uncompiled parser, our compiler, our interpreter are all running without a lot of optimizations. So if we look back at our JRuby architecture, one of the tricks we have is the --dev flag. The dev flag basically turns off a lot of extra optimization that you may not need when doing local development. It doesn't compile Ruby code into JVM bytecode, and it turns off some of the more aggressive optimizations at the JVM level. This gives us a pretty good improvement here. It's not where we would want to be, but we are starting to look better for a baseline case like -E1. If you actually run something larger, like generating a whole Rails application, now we start to look a little bit more competitive with JRuby. Here we're taking 2.7 seconds. Yes, this is still like 9 times slower than it takes JRuby to do it, but you can see that the dev mode is helping quite a bit. And the larger your application, the more work that it needs to do as it starts up, the more that JRuby will start to get closer to JRuby's time. So there's some newer features out in the JVM world we're looking into. One of them is called checkpoint and restore. This is a way of letting JRuby and the JVM run for a little while and then save off a checkpoint, a snapshot of that warmed up application. The implementation on Linux is called CRIU, checkpoint and restore in user space. This is integrated into one of the IBM JDKs, and it does work with JRuby. I have played around with it a bit. There is a new project, CRACK, which also is an acronym for checkpointing and restoring. This is eventually to be official OpenJDK support for checkpoint and restore. Hopefully this can be cross-platform and standardized, but I've got a little bit of an example here to show. So back to our -E1 example, if we use checkpointing to save off the warmed up JRuby, now we're getting much closer to JRuby. Here only less than 4 times slower, 3-ish to 4-ish times slower. And then, of course, a larger application. Now we're in the neighborhood of 2 to 3 times slower to get that started. So there's a lot more work that we can do here. We believe we can get these numbers down much closer to JRuby. So if you're running on Linux, we do have some answers coming. All right, another difficult area for JRuby has been implementing fibers. So fibers are called by many different names. We know them as fibers in the Ruby community, but Other runtimes, other communities call them virtual threads or threadlets or coroutines or Go routines if you're on Go. They're basically little micro threads. That's one way to look at them. So comparing this with threads depend on the operating system to switch from one to the next. If a thread makes a network call and the data isn't ready, then the operating system needs to see that thread is blocked on I/O, take it off of the CPU and put another one there to get some work done. If you end up with a bunch of threads that are all blocked, nobody can get anywhere. Now, the difference with fibers is that we can explicitly switch to another microthread, to another call stack without leaving the CPU, without the operating system even having to be involved. Allows us to have finer grained concurrency. When we know we're going to make a blocking call, we can schedule a different fiber to do some work while we're waiting for that data. This can also switch automatically. Fibers on JRuby can be configured so that if they do a blocking call, they don't get the data back, then we know immediately that we can schedule another fiber and it will start doing work. Or if you are locking on some resource and you need to wait for that, another fiber can jump in and take advantage of that CPU while we're waiting. So we also can do many fibers to one operating system thread, so there's fewer resources needed. By not having to spin up a separate thread for each of these little operations we want to do, we don't use as much of the system's memory. So this is kind of complicated to just talk through. So here's a graphical example. Here's our example with our execution flow going from top to bottom here. So here is our threaded example. We've got our thread number 1, not using fibers, just plain old threaded request handling. So we accept a socket, and now we're waiting for data to come off of that socket. While we're waiting for that data, the CPU, the operating system, is going to detect that we are not making any progress, we're not doing any work. The thread's going to get descheduled. That CPU is going to go to somebody else, and we're not getting work done on that processor anymore. Eventually, though, the data is available on the network. We can handle the request, get our response sent back, and now we need to make sure that they got the response and see if there's any additional requests that they need us to handle. And so this continues on. You can see how a simple threaded approach to request handling will waste a lot of time and possibly not get the most out of your CPU. So let's look at a fiber example. So here we have our other thread, and we're going to use fibers. So fiber number 1, this one's going to accept a socket. It's going to wait for I/O. Oh, but wait, we can see that we're going to be waiting for I/O. Why don't we start up another fiber, let that handle a separate request? So that one accepts a socket. That one starts to wait for I/O. By now, the first fiber's data is available, so it can handle the request, it can send the response, and so on from there. We're able to multiplex access to that same CPU without requiring the operating system to get involved and without requiring the resource overhead of a whole additional native thread. So on JRuby, traditionally, there's no fiber support. There hasn't been fiber support on the JVM. We've had to implement them with threads, native threads. And so you get the feeling and the behavior of fibers, but it's extremely resource intensive. Could really run no more than a few thousand fibers at a time, depending on what system you're on. Switching from fiber to fiber is not a direct handoff. It's standard context switching, just like regular threads. So we're at the mercy of the operating system and the CPU to run our fiber. Now, with the Ruby world rapidly moving towards having large-scale applications with tens of thousands or hundreds of thousands of fibers, this is clearly not going to scale for JRuby. Let's look at an example of how this affects us. So here is a little benchmark. We're going to spin up 100,000 fibers, make sure they're up and running, and then resume and complete all 100,000. We'll see how long that takes. Well, of course, on JRuby without native fiber support, boom, we're dead. We're very quickly going to kill the JVM with all of the fibers that we had to spin up. There's just no way that it can handle that number of fibers or that number of threads, and we're not even able to run the benchmark. So unhappy with this. This is what we run into with some of the modern Ruby applications when we don't have native fiber support. But there's good news here. Project Loom. So Project Loom is a OpenJDK project that is now shipping as of last August or so, last September in JDK 21. So like I said, JRuby's fibers are based on threads. If we use too many, they blow up. But Loom brings real fibers to the JVM level, native virtual threads that we can map our fibers directly onto. This actually turns out to be a very direct mapping, a simple mapping. And in fact, the use of fibers in JRuby was part of the inspiration for adding this feature to OpenJDK. So let's go back to our example. We've got our script here where we're going to create 100,000 fibers. Boom, right? So it blew up before. We don't like this. This is what we're trying to fix. So I went in once we actually had virtual threads in the JVM, decided immediately that I wanted to try to integrate this, got all set to do lots of work to integrate virtual threading into JRuby, and to my surprise, it was basically one line of code. So rather than calling out to our fiber executor, which was just a standard thread pool for fibers, we just ask the JVM to give us a virtual thread and start it with the contents of our fiber. All that was required, everything started to work much better. So what happens when we run our benchmark now? We actually get really good performance. And this is very much competitive with JRuby. Still have some optimization work to do here, and we're still working with Project Loom folks to make this even faster. So you might have heard talks from iAquatics, from Samuel, about running async and his Falcon web server to get 100,000 connections or 1 million connections live on a single instance of JRuby. This is now absolutely feasible on JRuby. You just saw we could spin up 100,000 fibers. If we configure the system to allow 100,000 sockets, we've got C100K running on JRuby. Still a bit more work here. The fiber scheduler and buffer APIs are shipping with JRuby, but still a little experimental. If you're interested in this, it's a great way for you to jump in and contribute. So another tricky area for JRuby is native libraries. So I mentioned we don't support regular Ruby's C extensions, and that limits us a bit. There's thousands of native libraries out there. Ruby developers want to be able to call those native functions, to be able to deal with native objects, native memory from those libraries. And typically, Ruby applications would use a C extension to do this. If we want to do the same, we need a different solution. So now Java has a similar extension API called the Java Native Interface. We could do the C extension approach and write a JNI wrapper around each of these libraries, but it's a great amount of work to write Java Native Interface libraries, and we don't want to have to do this and build on each platform. Part of the benefit of JRuby is Java's write once, run anywhere. We'd ideally like to avoid having to build native code every time you install a new JRuby application. So what if we can just do this dynamically at runtime? In JRuby, we have built a platform called the Java Native Runtime. Java Native Runtime provides a way to use the FFI library, the libffi foreign function interface, to load and call C libraries dynamically. without writing any C code, without running any compiler. On top of that, we build the JNR FFI API for binding these libraries. We have several common POSIX functions bound, which JRuby uses internally to have better compatibility with CRuby. And then a couple additional libraries like bringing native I/O into the JVM in a way that it recognizes it as a standard I/O channel, an implementation of Unix sockets so that JRuby can do Unix sockets long before any other JVM code could. It's structured sort of like this. So up at the top, you have some user code, probably calling through the JNR FFI library. That calls into the JFFI stub, which is a JNI library. So there's a bit of Java code and a bit of C code. That calls into libFFI, and then we finally reach our target library. So without having to rewrite any of those C pieces, you can actually call out to native functions, manipulate native memory, and integrate with all of the libraries out there in the native world. Now, you notice here, we're still using JNI for this. There are still problems with using JNI, even if we don't have to rewrite it. Crossing that boundary takes a lot of work. You saw that there's many steps, many layers in that transition just to make a call into a simple C function. The JVM itself also can't really optimize around JNI. It has to assume that it's a blank slate. It's an opaque call down into native code, and so it can't inline code, can't make those calls fast. And it's just a part of the design and part of the way that JNI works to isolate native code from the JVM. And then, as I mentioned, you still have to write and build and release these JNI bindings. We don't want to avoid that too. So here to the rescue is Project Panama. Project Panama is an open JDK project that brings a native foreign function interface to the JVM. So we have our FFI for calling down into libraries and making direct calls to C functions. We have a foreign memory API that optimizes calls from Ruby code or JVM code into the native heap, into native objects, so that can run much faster and have a well-managed life cycle. And it also comes with an interesting tool for extracting code from C and C++ headers. So not only do we not have to write the native code, we don't even have to write the Java code or the Ruby code to bind these libraries. Just point it at a C header file, and you've got a working interface to that library. There's two examples out there that I know are currently experimenting with this. JRuby uses the SQLite JDBC adapter, that's Java database connectivity. It just wraps the native SQLite. And of course, traditionally, it uses Java native interface. Works well enough, but there are throughput limitations. They have a proof of concept using Panama to bind SQLite. And on the examples I've seen, they're getting 2 to 3 times performance just by getting JNI out of it and using Panama. You may also have heard of the Prism parser. This is a new C-based Ruby language parser that all of the Ruby implementations can share. We already are working to integrate it. We've got most of the nodes implemented. The vast majority of Ruby language support is already done, and you can actually use Prism on JRuby 9.4. Currently still using JNI and our JNR wrapper around it, but this also will be considerably faster once we hook it up to Panama and use that to call down. All right, so let's talk a little bit about the future of JRuby. JRuby 9.4, as I mentioned, is still the current major release that we have. Continuing to stabilize, continuing to find and fix minor compatibility issues, moving towards more of a maintenance mode at this point. It's very stable, and we strongly recommend that you give it a shot and upgrade if you haven't upgraded your JRuby applications. There's lots of new JVM features that are coming out. I've mentioned Project Loom, Project Panama, Project Crack. There's also work on ahead of time compiling to speed up the startup time. There's work on adding new concurrency models built on top of virtual threads. So who knows what comes next? We're really excited about the JVM. But for JRuby, we do have one big announcement. JRuby 10 is coming out very soon. This is going to be a huge leap forward for us. Hoping to release it this year. We've already got a large part of Ruby 3.4 features complete, and we're tracking what's being done on CRuby master right now. We're going to require a minimum of at least Java 17, possibly Java 21, so that we can guarantee we have support for virtual threads and some of these newer features. Of course, we will be using the Prism parser, which allows us to keep up on language compatibility. Lots of optimization work. Being caught up on Ruby 3.4 compatibility has given me more time to step back and do some really cool optimizations. Hope that I can talk about those a little bit more later this year. This is definitely our biggest jump since the JRuby 9.0 or 9000 cycle. So hopefully we can get you to jump in and contribute. Of course, JRuby 10, we've thought about trying to call it JRuby X, but for obvious reasons these days, X is not a popular brand, so JRuby 10 it is. All right, so how can you help? Well, there are still many little features of Ruby 3.2, 3.3, and 3.4 that have not yet been implemented. You can add these. Even if you just want to write them in Ruby and contribute them, that's totally fine. We have part of JRuby that's implemented in Ruby. You can help implement features, and if we need to do more for performance later, we can deal with that then. You could start running JRuby 10 development builds. Test out your libraries, try out your applications. Let us know if you run into anything. You can jump into our bug tracker, which has 700 some open bugs. I guarantee most of those bugs probably are not valid anymore, but it's a big job to go in and look for the old bugs and clean them out. We really want to work with you. We are standing by. We have our chat room that I'll on Matrix. You can come to the Matrix chat room for JRuby. This is our website, and I think that's about all I have. Again, here's my contact information. You can find us on our Matrix channel by going to jruby.org and click on Community. Please jump into the project, message me on any of the services, or send me an email. I really love working with JRuby contributors, and I hope you'll have some fun in the process. Thanks very much.